This video will wrap up, yes, wrap up, finish our discussion of substitution and elimination reactions. They're never going away. Uh, you're always going to need to be looking out for them and thinking about them, but we're going to move on to a new topic after this. So we'll be thinking about epoxides in substitution reactions. They're going to act as electrophiles, as electron poor species, and they will be opened up by a nucleophile to generate a species like this. Then we'll think about alkynes, and we're going to think about alkynes in two contexts. We're going to think about an E2 reaction to form an alkyne, right? We were able to make alkenes via elimination of one equivalent of HBr. So how we make an alkyne with two pi bonds? Yes, elimination of two equivalents of HBr. So we're going to look at that. And then in the second context that we'll be thinking about alkynes and substitution and elimination reactions is actually the deprotonated form as a nucleophile. Yes, that can react with electrophiles in SN2 reactions. Here are our learning goals for today. Pause and take a look if you like. I am not going to read them because I just gave you a lengthy preamble in our intro slide. So let's get right to it. We'll think about epoxide openings. I would like for you to take a look at this reaction. You have not encountered it before. And I'd like for you to go through all these steps of analysis. I am not going to read them, but pause and give this a shot. So let's think about what's happening overall here. So we can see that we are breaking this bond. One of these carbon-oxygen bonds is being broken, and we're making this carbon-chlorine bond. So a CO bond will be broken, a carbon-chlorine bond will be made, and then we can also see we've made an OH bond. So we should protonate oxygen, aka make the OH bond. So those three things need to happen. And as far as what order they happen in, we're going to think really carefully about that. I can tell you it definitely does not happen first. We're not protonating first. And that's because there's no acid here. So don't be tempted to protonate oxygen. We can't. There's no acid. That leaves making the carbon-chlorine bond and breaking the carbon-oxygen bond. I can tell you we will also not be breaking this carbon-oxygen bond first. Think about that. We'll leave it circled, but we're definitely not doing it first. If we just break that carbon-oxygen bond, what have we done? Okay, well, we made a primary carbocation, and we have an awful leaving group. So, no, that's not going to happen on its own first. No way. So what is left? Well, to make the carbon-chlorine bond, and if it's not going to happen by an SN1, maybe it'll happen by an SN2, and that's a primary carbon, so the SN2 looks pretty good. So let's use a homolumo analysis. We can be pretty sure due to the negative charge on chloride, plus we're recognizing now that chloride is a nucleophile. So this is going to act as our electron-rich species using its HOMO, which is its non-bonding pair of electrons. It's a little bit unclear what the LUMO is, what the acceptor is for this ion, and it doesn't really matter because it's not going to act with its LUMO. It's going to act with its donor, and it's going to donate to the acceptor of the electrophile. So the epoxide here is the electron poor species. It's going to react through sigma star CO. And this is really good news. You may not realize it, but when we make the carbon-chlorine bond, oops, that's going to break the carbon-oxygen bond, right? When you fill sigma star, it breaks the sigma. So good, I think we're ready to do the mechanism, start the mechanism. We're going to have the electron-rich species attack the electron-poor species. So here we go. We have chloride ion going to fill up sigma star CO, and that breaks the sigma CO. We'll generate an intermediate that looks like this. And of course, that was an SN2 reaction. That was a bimolecular nucleophilic substitution. So we generate this alkoxide-looking intermediate. And what do you think that will do? Yeah, now it's time to make the OH bond. We didn't start by making the OH bond because we didn't have an acid, but now we have a base. So this is basic. And water can act as an acid. That's why it's there. It's the proton source. I labeled it as a proton source on the previous slide, but then I didn't really follow up on that. So it's donating the proton here. All right, let's go ahead and show that. So there's a final proton transfer step to generate the product. No problem, right? Electron-rich species attacks the electron-poor species in an SN2 reaction. Now this is a little bit weird because the leaving group would be the O- and it doesn't really leave. Also, this is not a good leaving group, right? It's a strong base. So why does this SN2 even happen? Well, it happens because in this first step, the SN2 reaction relieves the ring strain associated with the three-membered ring. So that's the driving force for this for this process. Otherwise, I mean, chloride's a relatively weak nucleophile. So otherwise, it's a little bit confusing. Weak nucleophile, bad leaving group, but it's because you're relieving the ring strain. So the ring strain is released here. We have this alkoxide intermediate, and then it gets protonated by water to form the nice neutral product. Let's take a look at the functional group in the product. This is called a halohydrin. So a halohydrin. Halo for the halogen, hydrogen for the water, for the OH. And in fact, it's called a vicinal halohydrin. Vicinal means that they have a 1-2 relationship. So vicinal halohydrin, vicinal means 1-2 relationship, vicinal, vicinity, neighbors. Let's keep going. All right, let's take a look at this one. So I would like for you to propose a mechanism for this transformation. And I want you to stick to the process that we just employed. The same overall 3 steps or things need to happen as in the previous example. The CO bond must be broken. It's not there anymore in the product, right? Then, or I'm not trying to imply order, this CO bond must be made. And this oxygen-hydrogen bond must also be made. So we must protonate oxygen. We're in a similar situation to last time where we have a negatively charged nucleophile. We have a primary carbon to the epoxide that's being broken. And so we're pretty sure this is going to be an SN2 reaction mechanism. So let's take a look. We have the alkoxide, which is delivered by sodium methoxide here. It is the electron-rich species. It does donate its electron pair to sigma star CO. Fill up sigma star, break sigma. That electron pair goes to oxygen. So the yellow electrons, those made the carbon-oxygen bond. The electrons in this bond, they end up as a lone pair on oxygen. That generates the alkoxide. Again, the alkoxide is a poor leaving group, but the ring strain was relieved in the three-membered ring. So that was the driving force for this step. Now the alkoxide is pretty basic and it's going to react with methanol. That is why methanol was listed as the solvent here. It's the proton source. And it's pretty typical that the conjugate acid of the nucleophile is used as the proton source in reactions like this. Okay, so then we have these electrons being donated to sigma star OH right here. Fill up sigma star, break sigma, this bond breaks, and then we will end up with regenerating alkoxide, the alkoxide, and forming the desired product. We can see once again in the product there's this 1-2 relationship of the nucleophile and the oxygen of the epoxide. That left one carbon, but doesn't leave the other. This reaction happens under basic conditions. Sodium methoxide is a base. If we want to define what I mean by basic conditions, I mean that the pKa of its conjugate acid, which in this case is the alcohol, it's 16. So any nucleophile that has a pKa, its conjugate acid has a pKa of 16 or greater, then we're going to consider this basic conditions. This is a similar metric to what we use to think about strong bases and the E2. All right, and then we saw this SN2 ring opening under basic conditions. The first example we looked at with chloride, these were considered neutral conditions. We did have an anionic nucleophile, just as we did with methoxide, but it's a weak base. It's just a good nucleophile. So for halogens, for halides, these are really considered neutral conditions. But the neutral conditions with the halide and the basic conditions with the alkoxide went by the same exact sets of elementary steps, SN2 and then proton transfer. Let's go ahead and describe the patterns represented by these two transformations. So the one under basic conditions and the one under neutral conditions as best as we can. In both cases, we have an epoxide acting as the electrophile and with an anionic nucleophile. There is some solvent or proton source. So for the base under basic conditions, it was the conjugate acid of the base. And then for the neutral conditions, it was from water, but there's some proton source. And then finally, you have the ring opened epoxide. And you have, in both cases, this 1-2 relationship between the alcohol and the nucleophile that attacked the epoxide. These reactions go by the same two steps, SN2 and then proton transfer. The SN2 breaks the CO bond and makes the carbon nucleophile bond at the same time, and then the proton transfer neutralizes the alkoxide intermediate. So what do you suppose the rate law is for the substitutions of epoxides that proceed by this mechanism? Well, yes, it's an SN2, so the rate law should be little k, rate constant K, times the concentration of the epoxide times the concentration of the nucleophile. What do you suppose would make for the fastest type of this reaction? Well, both the electrophile and the nucleophile are in the rate law, so let's take a look at both. Certainly, we've been looking at ethylene oxide. Both of these carbons are primary, so this would be our fastest electrophile, the most easy for the nucleophile to get in there and attack the sigma star CO. And then you could imagine that this an epoxide like this might also be pretty reactive, where you have a primary and a secondary carbon. Certainly, you would have attack at the primary carbon because it's less substituted, and this beta branching adjacent to it would slow down the SN2. But relieving that ring strain is just such a driving force that we still will have SN2 reactions of epoxides, such as this one, to generate products like this. Okay, so fastest, second fastest, and then let's think about the nucleophiles. Well, nucleophiles also in the rate law. This is just, for the nucleophile, it's just going to follow the trends for SN2 nucleophilicity because it is an SN2 reaction. So follows what you learned for SN2. So the highest energy lone pairs make for the best nucleophiles. And we could brainstorm some good nucleophiles for SN2, and we're going to do that actually in just a second. All right, finally, how are epoxides different than alkyl halides or tosylates in the context of these reactions? So an epoxide versus an alkyl halide or a tosylate, what do we think here? Well, the epoxide has ring strain. When the epoxide is opened, the leaving group doesn't really leave, right? We go from here to from the epoxide to having the leaving group sort of still as part of the molecule because that bond didn't break. Whereas for, say, a tosylate, you would have, let's have a nucleophile attack, tosylate leaves, you have a substitution product and the tosylate leaving. So that's a difference for sure. Anything else you can think of? Yes, the epoxide has two possible reactive sites, both of those CO bonds. All right. So let's get back to this issue of what nucleophiles might be involved in SN2 reactions of epoxides. So let's think of some nucleophiles that you are aware of. So pause and brainstorm. Yeah, so you could have cyanide. What are some other excellent nucleophiles? Thiolates, awesome. Azides. Anything else? So those we have, and then alkoxides, obviously, we looked at. We could look at halides. So all of these would definitely go by this neutral or basic mechanism. So these are some anionic nucleophiles. Remember we said for both of those types of reactions, a nucleophile is anionic. You might be wondering, will neutral nucleophiles react in this reaction or react with epoxides by an SN2? Like, for example, instead of using methoxide, could you use methanol? No, they won't react yet. I'm going to show you later, but they won't react yet. You're going to need something. It's going to require some catalyst, or you're going to need something here. Because this is a weak nucleophile. This is a weak electrophile. They're both weak. Nothing happens. So right now, no, not yet. We can't use neutral nucleophiles yet. So we're going to stay focused on anionic nucleophiles for now that will react by this scheme. So SN2 and then proton transfer. And if for some reason you have a epoxide like this, where it's asymmetric, the primary carbon will be more reactive because it's just a better SN2 substrate. We're going to think about some new nucleophiles now, ones that we have not encountered, or we have encountered them, but we haven't talked about them very much. So the first one that we'll discuss is called an acetylide ion. So an acetylide ion is related to acetylene. The "ide" lets you know that it is an anion, right? So this is an acetylide ion. It's a carbon-based nucleophile. It should remind you of cyanide a little bit. And you know cyanide is an excellent nucleophile. So I bet the acetylide ion is too. You might wonder, well, how do you make these? I'm going to show you, but I'll give you a little bit of a preview. So you just start from a terminal alkyne. and you're going to treat it with some base. Okay, so acetylide ions. These could be nucleophiles to open up epoxides. Now let's move to some unfamiliar looking reagents. So lithium aluminum hydride, which we'll call LAH, lithium aluminum hydride. It can also act as a nucleophile in these reactions, these epoxide opening reactions. All right, that's fun. So we're going to talk so much about this reagent moving forward this semester and next semester, but it donates hydride. And you can think about it two ways. You can just say, I'm going to pretend it's hydride and have hydride attack, or you can do it really happens. It attacks from its sigma ALH, aluminum hydrogen electrons. Either way, so the simple version or the not simple version. But the bottom line is it's going to donate hydride no matter how you end up drawing the mechanism. Grignard reagents and organolithium reagents are examples of organometallic reagents, and these deliver carbon ions. We will look at an example of both of these. So Grignard reagent, the simplest way to represent it is R, Mg, Br. You can think about it as a carbon ion with a magnesium counterion and a bromide counterion. So overall, the charges balance out. I've drawn it here like an ionic bond. I can draw it here like a covalent bond. Really, it's somewhere in between. The bond is somewhere in between a covalent bond and an ionic bond. It's an area of gray. So we can look at an example. We can look at ethyl Grignard. Grignard is just the name of one of the people who discovered this reagent. Okay, so here are those electrons, those nucleophilic electrons. So we can think about ethyl Grignard like this if we want, with an anionic carbon and then magnesium, bromide. Okay, and then finally the organolithium. It's really similar to the Grignard reagent, the organomagnesium reagent. Or you can think about it like a lithium cation and a carbon ion. We can look again at ethyl lithium. And we can think about these electrons. These are the nucleophilic ones. Okay, and we can think about the reagent like this. Now, before I forget here, all of these reagents, they're really basic. So all of these are pretty basic. So you'll need to keep them away. There's probably a more technical term, but my brain just can't right now. From acidic protons. And even mildly acidic protons. So this includes water and alcohols. They have pKa's of 16. If you think about the conjugate acid of the acetylide ion, for example, this has a pKa of 25-ish, 24, 25. So it's definitely a weaker acid than the alcohol. So you want to keep these reagents away from proton sources such as water and alcohols. So that you might imagine that can be an issue because we have proton sources in these reactions. It's no big deal. What you're going to see is there's going to be a step 1 where you use the basic nucleophile and the super basic one, and then a step 2 where you use a proton source. Okay. Cool. So we're going to try to use these. So let's pause now, and I would like for you to propose a complete curved arrow mechanism for this transformation. There's an epoxide, which will react as the electrophile. We have an anionic nucleophile. Now, this anionic nucleophile is really basic, meaning that its conjugate acid has a pKa greater than 16. So we must exclude water and other proton sources from the step with the nucleophile. So there's this separate workup step. It's like an extraction and it essentially, or a neutralization that you've done in lab. And this separate workup step will serve as our proton source. But we have to use it after we have allowed the really basic nucleophile to react with the epoxide. We can see that this bond is broken, and that makes, so it's not here anymore. That makes sense because this reaction proceeds by an SN2 mechanism, and the primary carbon is more reactive to SN2. It is easier. There was a lower activation barrier for the nucleophile to get into that carbon and attack. And then we notice that this is a chiral epoxide. Here's the stereogenic center, but nothing has happened to it, right? There'll be no reaction there. The carbon that reacts is the yet one that I've highlighted in yellow, the primary carbon. So you notice the stereochemistry doesn't change. So it is an SN, this is overall going to be an SN2, but an SN2 at the primary carbon, this carbon, where there's no stereochemistry. So you just can't tell. All right, if that didn't make any sense, well, let's just look at the mechanism and that should help. So look down at the bottom here. We have the anionic nucleophile, the acetylide ion, donating its non-bonding pair of electrons on carbon to sigma star CO. Fill a sigma star, break a sigma, and then those electrons will go on to oxygen. Okay, so now we have broken the bond between oxygen, it's not there anymore, and the primary carbon. So we're halfway there, right? Okay, so we broke this bond. Now, we have generated the alkoxide, and it's time to protonate. So now we would, if we were in lab, we would neutralize the reaction by adding hydrochloric acid, dropwise and carefully, until we were at acidic pH. So for the neutralization with hydrochloric acid, you can see I'm showing hydronium as the acid, and that's because as soon as you put HCl in water, it protonates water, as you know from Chem 1B, and so it is hydronium that we have in solution. If you want to use HCl, that's fine, but technically it's hydronium. All right, so go ahead, protonate to generate the OH bond, and we have the product. Same exact steps as before. SN2, proton transfer. But for this pretty basic nucleophile, where it has a conjugate acid with a pKa of greater than 16, recall we said terminal alkyne, the pKa is 25. So because of that, we have to keep it separate from the proton source. So once the attack has occurred, then you add the acid. But it's still SN2, proton transfer. Let's pause and predict the products of each of these reactions. You notice that for each of these reactions, the epoxide is being treated with an anionic nucleophile. So that tells us that we will observe SN2 at the less substituted carbon, because that carbon will have the fastest rate of SN2, as we know. Of course, for this epoxide, the carbons are the same, but let's say we had this epoxide. You would see a substitution of the less substituted carbon followed by proton transfer. Okay, so let's go ahead and look at the answers. So I have all the mechanisms drawn out. Every time it'll be SN2, proton transfer, SN2, proton transfer, etc., etc. For the products, you will see this 1-2 relationship of the new bond to the nucleophile and the original hydroxyl from the epoxide. All right. Now let's consider the rates of these reactions. So pause for a moment and choose the reaction in each pair with the fastest rate, and be sure to explain your answer. These reactions go by SN2 mechanisms, so we do observe both the epoxide and the nucleophile in the rate law. So the difference between The first set of reactions would be the beta branching for that epoxide. So certainly the cyanide nucleophile attacks a primary carbon in both cases. But for the case of this epoxide, the beta carbon has these two substituents, and we know that beta branching slows down SN2. Thus, the faster reaction will be this one on the left. Next reaction, we have chloride versus bromide. So in the first example, we observe the epoxide sterics affecting the rate, steric profile. In the second reaction, we'll observe nucleophile strength affecting the rate. So bromide is a better nucleophile than chloride, and so the second reaction will be faster. All right, let's keep going. So for these examples, we're going to examine more complicated epoxides, meaning not just this one. This one's called ethylene oxide. So we're looking beyond ethylene oxide. So let's predict the products of these reactions. So go ahead and pause. So each of these examples is under basic conditions where there's an anionic nucleophile. So for the first example, the anionic nucleophile is ethoxide. It will engage in an SN2 reaction with the epoxide, and then after proton transfer, we'll end up with the product shown. Nothing happens at the stereocenter, right? The stereocenter stays the same. Nothing happened here. That's because SN2 will occur at the less sterically hindered carbon. Next example, the nucleophile is azide. And again, an SN2 will occur at the less sterically hindered carbon. And then after proton transfer, we observe the product shown. Let's go up here. For this reaction, recall that lithium aluminum hydride donates hydride. Hydride will react at the less substituted carbon. So here's this hydride. We went from CH2 to CH3. And this is a hard one. Here, let's actually make that proton pink. Make hydride pink, and we'll make the proton from the workup yellow. All right, super. In this final example, the epoxide is treated with a Grignard reagent. Grignard reagents are these organomagnesium reagents. And we can pretend that this reagent is a carbanion, and you can think about it reacting the way that I've drawn with the curved arrows. Now, in reality, that carbon-magnesium bond is somewhere in between covalent and ionic. So you could think about it as a pure carbanion, or you could have the electrons from the magnesium-carbon bond doing the attacking. But either way, we have this SN2 reaction to end up with this trans relationship here between the two bonds, the one that we made between carbon 1 and the Grignard, and the remaining carbon-oxygen bond from the epoxide. And that's because this SN2 attack will go with inversion. It does happen from behind the carbon-oxygen bond. And then, of course, there's protonation in a separate workup step. So just keep in mind here, one last thing. These last two examples, they have a separate workup step because the anionic nucleophiles are so basic, you have to keep them away from water. This last reaction in particular is very useful because it generates this new carbon-carbon bond. We're going to pause now to think about our synthetic toolbox. As organic chemists, we will need to make organic molecules, or at least make them on paper. And in most cases, this will require an electrophilic, electron-poor source of carbon and a nucleophilic, electron-rich source of carbon. So take a moment and list the electrophilic and nucleophilic sources of carbon that you know. Well, today we're talking about epoxides, and those are electron-poor sources of carbon. In previous classes, we've discussed alkyl halides and alkyl tosylates. How about electron-rich carbon? Okay. Well, we have cyanide. It's probably the first example of nucleophilic carbon that we learned. Today we've learned the acetylide ion, so made from a terminal alkyne. Looks a lot like cyanide. Enolates we have learned recently, or enols. Anything else? Yes, on the previous page we learned about Grignard reagents, which deliver carbon ions. We could also use an organolithium reagent here to deliver a carbon ion. These carbon ions are usually more basic than nucleophilic, but you can use them as nucleophiles in some contexts. They will not, however, they will not react with alkyl halides. So actually, maybe I'll write that down. So they're basic and react with epoxides and substitution reactions, but not with alkyl halides. With alkyl halides, they would just do an elimination. All right, let's move on. So we're going to think more about these acetylide ions that we made from terminal alkynes. Before we get to that, let's take a look at this transformation. Why don't you pause and try this one? So in this example, a vinyl halide is being converted to a terminal alkyne. We can see that HBr is eliminated from the molecule, and we have sodium hydroxide, which is a base. So as for what happens here, I need to move this out of my way, huh? For what happens here, hydroxide deprotonates the beta to the leaving group. And then what do you think happens? Yes, the electrons in this bond form the triple bond, and bromide leaves as a leaving group. So what is this reaction called? Yes, this is an E2. This is an E2 reaction. We still observe this anti-elimination. And I've drawn it as an anti-elimination because of that. So anti, or the sigma CH, needs to be anti-periplanar to sigma star CBr. Because recall, so what we have, what I'm showing here is non-bonding oxygen attacking sigma star CH, and then those sigma electrons, so filling sigma star breaks sigma, and then these sigma electrons, they need to fill up sigma star CBr to break that CBr bond. All right, cool. So what is the bottom line here? Alkynes, terminal alkynes, but alkynes in general, can be made from elimination of vinyl halides, and we use a strong base, just like you already know for E2. Here are some different examples of generating alkynes via E2 elimination reactions. You can see the first one is what we just examined, the vinyl halide. I would like for you to go ahead and think about what types of functional groups I have here and what different bases we're using. Alkynes can be generated via E2 elimination reactions of a few different functional groups. So we've examined already elimination of HBr from a vinyl bromide to generate, in this case, the terminal alkyne, but this would also presumably work for an internal alkyne if this were some alkyl group. Okay, then this would be R, and you'd have an internal alkyne where it's in the middle of the carbon chain, like the next example. So the next example, we look at a vicinal dibromide. We'll eliminate 2 equivalents of HBr from this. So there's this equivalent of HBr and this equivalent of HBr to generate an internal alkyne this time. But could have just as easily generated a terminal alkyne if this had not been an alkyl group. All right, last example, we're looking at a geminal, a 1,1 dibromide, geminal, Gemini, twins, the two bromine substituents are on the same carbon here. So again, looking at eliminating 1 equivalent of HBr, 2 equivalents of HBr to generate, in this case, the internal alkyne. Okay, so these 3 functional groups can be used, and then as far as which bases, well, I've listed them here. Okay, so these are the bases that can be used. There are strong bases. I've also listed their conjugate acid pKa's just to demonstrate to you how weak their conjugate acids are, so how strong the bases are. Now, here's an example of from the previous page of this geminal dihalide being treated with sodium hydride to generate a terminal alkyne. And we can see that 2 equivalents of HBr, 1, 2, are eliminated from the molecule. So if 2 equivalents are eliminated, then why are 3 equivalents of sodium hydride needed here? Well, let's pause and attempt to answer this question. All right, so we have our first E2 elimination. To generate the vinyl bromide. Then what? Okay, we're going to have another elimination with a second equivalent of hydride. Okay. That will generate, well, it looks like it's the product, right? But we've used 1, 2 equivalents, 1, 2 equivalents of hydride, and we know we're going to use one more because that's what it says. So what's up here? Well, this is a terminal alkyne. And on the previous page, I used an internal alkyne on purpose. Okay, but the terminal, look at this example here, or this example here. I used these internal alkynes on purpose so we didn't have to deal with this issue. So this is specifically occurring because we have a terminal alkyne, and the pKa of this proton is 25, and the pKa of hydrogen gas, about 50. So what that means is that once the terminal alkyne is generated, it is going to react with another equivalent of hydride, no matter whether or not you want it to. So it reacts with that third equivalent to generate the acetylide ion. And now from here, we could actually just use the acetylide ion to do something if you wanted to. If you added some electrophile, it might react with it. But that's not what we wanted here. We wanted the terminal alkyne. So once you have generated the acetylide ion, then we just do the workup. So we do an extraction, or we add acid, or we neutralize in some way. In this case, I've used water, and that generates the terminal alkyne product. All right, so terminal alkynes, they have pKa's of 25, so they're perfectly stable around hydroxide. Hydroxide doesn't appreciably deprotonate them, but amide, NH2, and hydride, they will, because their conjugate acids are weaker than the terminal alkyne. Okay, so that I'll repeat that one more time. When you are generating a terminal alkyne and you use sodium hydride or sodium amide, you'll need to do a workup step. I mentioned once the acetylide ion is generated, instead of the workup step to just install this proton, make the terminal alkyne, you might want to keep reacting the acetylide ion with some electrophile and make some different products, different functional groups. So here there's two examples of that. Instead of a workup, once the acetylide ion is generated in step 1, we'll treat with an epoxide. And instead of a workup, well, in this one, we already have a terminal alkyne. So in this example, we're just taking a terminal alkyne, deprotonating it, and then treating with an alkyl halide. So let's take a look. I want you to draw out the complete curved arrow mechanisms. I'm just going to show you the key intermediates to help you along. So you're going to do this on your own. Spoiler alert, it's on the previous page. Okay, so this is our acetylide intermediate. So now we can treat it with the epoxide. And then after the workup, we would observe this. Nope, we would observe this product. Okay, don't panic. So you're going to work out the whole mechanism. In fact, maybe you just pause and go do that right now. This is the new bond, and these are the two carbons from the epoxide. Next example, so the terminal alkyne is deprotonated by sodium amide. This equilibrium constant is huge for this deprotonation because ammonia is generated, which has a pKa of about 35, and the terminal alkyne has a pKa of about 25, so 10 to the 10. And then you treat with the alkyl bromide, and we generate, ooh, that's fun, we generate this species. So let's highlight our carbon. So here from the terminal alkyne, making the acetylide ion, and then we have the two carbons from ethyl bromide. Cool, we made an internal alkyne. All right, make sure that you especially understand this reaction sequence here, right? So acetylide ions are really nucleophilic, and there's many ways to use them. They're excellent nucleophiles, and there are many ways to use them in chemical reactions that we already are aware of with electrophiles that we brainstormed on our synthetic toolbox slide somewhere. Yeah, all right. So we reacted epoxides and alkyl halides with acetylide ions. Okay, so here's some problems. I'm going to have you try these on your own and compare with what I have in the notes. Now's a good time or after you take a rest because this is getting long, huh? So we're going to go to our final topic. Our final topic is to return to epoxides. We took a little detour to consider carbon-based nucleophiles. We looked at acetylide ions. We looked at organolithium ions and organomagnesium ions. Certainly, acetylide ions are the most versatile of all of these carbon-based nucleophiles. And we already knew about enolates and cyanide. We thought about making alkynes via E2 elimination reactions. I showed you 3 different functional groups you could start with to do that. And then finally, we thought about terminal alkynes, again, to deprotonate them to generate these great nucleophiles, acetylide ions, and we saw reacting them. We examined reacting them with epoxides and alkyl halides to generate fun new products. Make sure that you can do that. Okay, so that's right here. Now we're going to return to thinking about epoxides and substitution reactions. At the beginning of this video, we talked about these reactions under basic conditions with anionic nucleophiles. And I asked you a question, which was, could you react epoxides with neutral nucleophiles? And at that time, we said no. And that was because we hadn't learned how yet. So I think we said not yet. Okay, so the time is now to learn how to do this. And it's instead of basic conditions, it will be under acidic conditions. Let's propose a complete curved arrow mechanism for this reaction. You can immediately see that we have a strong acid in solution. And then there's a neutral nucleophile. We can see that we are breaking, well, let's see, which bond are we breaking here? We are breaking this carbon-oxygen bond. So here's oxygen. There it is in the product. It forms the OH. Methanol has incorporated itself right here. Okay. So we can see that methanol has actually made a bond to what we will call carbon 2. Again, not nomenclature naming, just figuring stuff out naming. And what else can we see? We can see there's been inversion at carbon 2. So we can see attack at carbon 2 and inversion at carbon 2. Now this is weird because carbon 2 is the more substituted carbon. But we're observing a different type of mechanism here. All right, we're going to write that down. It's more substituted. Okay, let's go ahead and get started. So if there's a strong acid, we're going to protonate first. Under basic conditions, I said absolutely do not protonate first. There's no reason to do that. Well, under acidic conditions, there is, because you have a strong acid. Now, of course, when HCl is added to methanol, it immediately protonates methanol, just like it would immediately protonate water. And so we really have protonated methanol as the acid. If you would like to show HCl, that is certainly up to you. But I'm going to show protonated methanol as the acid because that reflects what's actually going on in solution. So this proton transfer reaction generates the protonated epoxide. And this is a really good, really strong, really reactive electrophile. Not only is there all that ring strain we talked about, there's a positive formal charge on oxygen. So now looking at what happens, looking at the products, we can see that methanol needs to attack, and it attacks carbon 2. So again, the protonated epoxide, it is really electron poor. Plus it has the ring strain. So it's really reactive. So that means it's going to react with this weak nucleophile methanol. That is our electron-rich species. Weak nucleophile methanol. And we can see methanol reacts at carbon 2 because we can see the product. It's not cheating, it's just what happens. So let's look at this. So this is we're proposing an SN2 mechanism, and I'm putting the question mark and the exclamation point because we're attacking the more substituted carbon, which typically we think does not happen. All right, so here we go. So here we have the intermediate, and then the intermediate will be deprotonated by methanol. Methanol is the base here, and generate this product. And we're showing an SN2, so this needs to occur with inversion of stereochemistry. And I've drawn the intermediate and the product in a different way. And so I just want to confirm for you and with you that I'm showing inversion correctly and that this molecule and this molecule are exactly the same. Well, other than the deprotonation, but the stereochemistry is the same. Okay, so I've taken the protonated epoxide and I've redrawn it down here because there's lots of numbers and I don't want it to get too confusing. So here's the stereocenter, and I've looked at the 3 atoms that are bonded to the stereocenter. So it's oxygen, and then it's these 2 carbons. The 2 carbons, they tie. So these 2 carbons tie. So the methyl group down here is bonded to HHH. The CH2 group is bonded to OHH. So OHH wins. So this carbon gets second priority. So then we trace the path. It's 1, 2, 3. That looks like S, but the lowest priority group is coming out. The H is coming out. So that means it's actually R. I'm doing the same thing on this stereocenter. And at that stereocenter, there should have been inversion, right? Because the nucleophile attacks here. So there should be an inversion at that stereocenter. So we expect it to be S in both the intermediate and the product. And in fact, I assign priorities in the intermediate, and it is S, so that's good. It should be inversion from R to S because the SN2 happens here between these 2 intermediates. And then the product should also be S because nothing has happened in between just deprotonating this protonated alcohol. So I have in fact shown correctly inversion of stereochemistry. All right, what in the world is going on here, right? Why do we observe SN1 regiochemistry, meaning that the more substituted carbon reacts under acidic conditions? But we're still observing SN2 stereochemistry. So we're seeing SN1 regiochemistry, which means that the more substituted carbon, carbon 2, was attacked by methanol, but we're still seeing inversion of stereochemistry, which is associated with SN2. Okay, let's look at this key intermediate. So this key intermediate, this protonated epoxide, the stress on it is that positive charge on oxygen. So what can happen, or what does happen, is that carbon shares the formal charge. It shares being electron poor with oxygen. And it does that through the more substituted of these 2 carbons. So if carbon 1 versus carbon 2 is more substituted. So the more substituted carbon shares the charge with oxygen just by virtue of having a longer bond to oxygen. So oxygen just pulls more of the electrons in this bond towards itself. So you can imagine just kind of a longer bond there. And that more substituted carbon shares the charge. And that's because the more substituted carbon is more stable doing so, right? If you think about carbocation stability, tertiary carbocation is more stable than a secondary or a primary carbocation. So that's no different here. We have a primary versus a secondary carbon, and the secondary carbon is just more stable sharing that charge. So this is what the protonated epoxide intermediate really looks like. It looks like it has shared the partial charge or the charge between these 2 atoms because carbon can help oxygen with that positive charge. So then when methanol, just weak nucleophile methanol, it wanders by, it is attracted to that positive partial charge on the more substituted carbon. So that explains why we see SN1 regiochemistry. Because the more substituted carbon, and this is only under neutral conditions, or excuse me, only under acidic conditions, the more substituted carbon is just sharing that positive charge with oxygen. So we see SN1 regiochemistry, but this bond isn't broken or anything, it's still there. So it's just longer. So we also observe SN2 stereochemistry. There's still inversion here when methanol attacks. But there's still it still goes by SN2. There's still inversion because this bond isn't fully broken, it's just long. And so that explains SN1 regiochemistry and SN2 stereochemistry. So there are two mechanistic pathways by which epoxides react. We are going to describe them, compare them, contrast them. This video is run super long, so you're gonna do some of this on your own. But very quickly, we have an acid, okay? So under acidic conditions, protonation occurs first. The protonated epoxide is the active electrophile. And we said really there's this buildup of positive charge on the more substituted carbon. So then this neutral nucleophile attacks the more substituted carbon with inversion. So we see a bond formed under acidic conditions to the more substituted carbon with inversion. Under basic conditions, what happens first is nucleophilic attack. The SN2 happens first. And it happens just in the classic, normal SN2 fashion, where you attack the less substituted carbon. If there was a stereocenter there, you would see inversion, but there's no stereocenter for this particular example. Now the other carbon is chiral, but there's no inversion there because nothing happened there. Okay, so nothing happened there. So if you have SN2 first to make the anionic intermediate, and then you'd have proton transfer. Okay, so you're going to do your practice problems. You're going to predict the products of these reactions. All of these are under acidic conditions. Acid, 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 and then you'll look at the answers in the notes. All right, there's a lot of practice problems here. And then finally, I really want you to summarize what you just learned. You're going to probably need to rewind this page and this page and this page a couple of times and make sure you understand the difference between acidic conditions and basic conditions, and that you can understand which pathway is happening if you encounter them in a problem like this. Okay, think about what you've learned today. It was a lot. Make sure that you revisit these learning goals. We summarized, about halfway through. Well, not halfway through. We summarized about 10 minutes ago. So if you want to hear the summary, you can go back and listen to that. All right, time to practice.